Bismillah ar-Rahman ar-Rahim. Welcome to tutorial number 7. And over here we have a number of questions. So let us start with the question number 1. Say that a single tone filter is tuned to the 11th harmonic. If XC equal to 650 ohm, find the following: the reactor size of the filter. Okay, so we need to find what will be XL. Okay, so what will be XL? So we know that, we know XC, we know H, therefore XL is equal to XC divided by the harmonic order, which is 11 square, so that will give XL. Okay, calculate the characteristics reactance of the filter XR. So we know that XR equal to the square root of XC times XL, and that will give us the characteristics reactance of the filter. Part C, he said, determine the size of the reactor resistance if the filter quality factor is 60, and of course this is single tone filter. We know that the quality factor, so the quality factor of the filter equals to XR, the characteristics reactance, divided by the resistance. Everything is given except R, and then we can calculate the value of R. Okay, and of course R will be equal to 0.985. For the second question, he say that what is the tuning order? So he like us to find H and the quality factor for the filter QF of 36 series tuned filter. Okay, so in this case we have a series tuned filter with XC equal to that, XL and R. Okay, so again, how to determine the tuning order or the harmonic order? So we know that the harmonic order will be equal to the square root of XC divided by XL. Okay, everything is given. We can find the tuning order. Okay, then the quality factor for the filter, quality factor for the filter will be the characteristics impedance for the filter divided by R, and XR can be obtained from XC times XL divided by R. So that will give us the quality factor. Okay, then he said also okay, so those are the values. Okay, then he said determine what will be the reactive power delivered by the capacitor bank, and what will be the size of the filter. So we like to calculate what will be Q for the capacitor bank and what will be the rated of the filter, because again the filter consists of L, C and R, right? So we like to find what will be the reactive power delivered by C, and then what will be the size for the whole filter. So what will be the Q for the whole filter? Well, the Q for the capacitor will be, of course, will be equal to the voltage square divided by XC. So we have the voltage square divided by XC, and the voltage is given to us as 36. XC is given also. Then we can find what will be the reactive power that will be provided by the capacitor. Now to find the reactive to find the size of the filter, so we need also to include the presence of L, right? Okay, so we know that of course the resistance will not consume any reactive power. It will not give, it will not consume. Therefore, for the whole filter, Q for the whole filter will be equal to the voltage square divided by XC minus question 3. We have 34.5 kilovolt single tune filter that has XC of that, XL of that. Determine the tuning order of the filter H. So we know that H will be equal to the square root of XC divided by XL. Okay, and that will give us that value. Determine the reactive power delivered by the capacitor bank. So it is V square over XC. That will be the value. Determine the rated size of the filter. So again, over here, this filter, the single tone filter, which consists of L and C, right? So there consists of L and C. So now we like to find what will be the size of this filter, of the whole filter. So we know that we can find the size of the filter from P square divided by XC minus XL, okay, which can be calculated as it is shown over here. Also XC minus XL, or we call it XF. So XF or XO of the filter, which is given as XC minus XL, can be written also as XC, and XL will be equal to XC over H square. Then you will take XC as a common, XC as a common. Then what will remain? What will remain if you take XC as a common? 1 minus 1 over H square, okay, which can be written as XC. Then over here we have H square minus 1 divided by H square, which is written over here. Okay, so we can also replace XC minus XL by XC H square minus 1 over H square as it is written over here, and then again V square over XC will be equal to Q of the capacitor. In question number 4, we have 34.5 kilovolt 6 megavolt ampere capacitor bank is being used as second order damped filter. So this is the second order filter, tuned to be more than or equal to 5. Determine the following: the size of the capacitor reactance. So we need to find XC. This is 3-phase. So we know the voltage, we know Q, then we can find XC, straightforward. Okay, so V square divided by QC, that will give us the size of the reactance of the capacitor. Okay, determine the size of the reactor. So we need to find XL. We know the harmonic order 5. We know XC. Then XL can be calculated as XC divided by H square, and that will give us 7.9. Okay, so we are done with that. part C, calculate the characteristics reactance of the filter. So we'll have to find what will be the characteristics reactance of the filter XR, which can be calculated from XC times XL, and that will give us this value 39.6 ohm. Part D, determine the size of the resistor bank for quality factors of 0.5, 2, 3, and 5. Okay, over here of course we have second order high pass filter, so to calculate the quality factor of that, so quality factor will be given as R divided by XR, okay, divided by the characteristics reactance of the filter, and of course we have a number of Q, then we can find the value of R for each Q. Okay, so 39 times 0.5 depend on the quality factor, and that will give us the value of the resistance. Then in part E, he said calculate the rated filter size. So again it will be V square over XC minus XL, or it can be calculated from again this equation that we have already proved, H square over H square minus 1 times QC, and that will give us 6.25. Okay, so this is with regard to the questions. Now we're gonna move to question number 5, and say that we have 1 megavolt ampere, 60 hertz, 13.2 kilovolts over 480 power transformer. Okay, so this is the size of the transformer with a short circuit reactance of 10%. Okay, so we have a transformer that has X per unit equal to 0.1. Can calculate the Z base, V square over, so 0.48 divided 0.48 divided by 1, 0.48 square divided by 1, that will give us Z base, multiply Z base times 0.1, that will give us the impedance of the transformer. Okay, and the transformer feeds this amount of power to a load. So the amount of power provided to the load is 699 kilowatt at 1405 ampere. Okay, at that voltage. Okay, and the load mainly consists of 6 pulse rectifier, and that of course that 6 pulse rectifier will inject fifth harmonic current, and the value of the fifth harmonic current is 30% of the fundamental current. Okay, and now he said design single tone fifth harmonic notch filter. So we need to design a filter to compensate the power factor to 0.95 lagging, and such that it will take care, it will absorb, or it will short out the fifth harmonic current. So this is what we need to do. We need to design this problem. We need to design a notch filter that will take care of the fifth harmonic, and also it will improve the power factor. Let us now calculate the initial power factor. So the power is given. Okay, so we have over here a source, we have a transformer, and over here we have a load. Okay, we have a load. So that load, this load take this amount of power, 9 3 kilowatt at a current of 1405 ampere, and the voltage level over here is 480. Okay, so then we can calculate, of course, the power factor. So we know that power is given as I root 3, because we have 3 phase, root 3 I B line cosine the angle between the voltage and the current, or cos theta 1. Power is given, voltage is given, the current is given. So from here we can calculate the power factor, and then we calculate theta 1. And now he said that we like also to connect over here a single tone filter. So we like to connect with the existing system. So we like to connect over here a filter that will take care of the fifth harmonic, and that also at the same time it will improve the power factor to 0.95 lagging. So the cosine theta 2 is 0.95, and then we can calculate theta 2 for the whole filter, of course. Okay, or so the power factor for the whole system was improved from cosine theta 1 to 0.95 lagging. Okay, so what we need to determine over here, we need to determine the value of C, we need to determine the value of L. Okay, so let us start with the filter itself, with the whole filter. So we know that this is the real power. If I draw the power triangle, this is P, this is Q. Okay, and now this is our theta 1 over here. And then of course we're able to improve the power factor by reducing the angle to theta 2 by connecting this filter. And now we like to find what will be the amount, or what will be the size of this filter. Okay, so how to do that? So then we can find the what will be the size of the filter. For this one, QF. So this one between there and there is a Q1. Okay, between there will be Q2, I will call it, or Q new, Q not theta, of course, this is a Q, okay, Q new. And then the difference between Q old and Q new will be Q that will be provided by the filter. So Q for the filter will be equal to Q old minus Q new, which is B tan theta 1 minus tan theta 2. So that will give us Q. Okay. And then of course, once we know QF, we can calculate what will be the overall impedance for the filter. So once we calculated this one, we can obtain XF for the filter, right? So XF for the filter will be equal to V square divided by QF. And that will give us XF, and of course XF will be XL minus XC. And again, we know that the relationship between XC and XL will be, we know that H, and that also H will be equal to the square root of XC over XL. Then we can calculate what will be the XC and XL as it is provided over here. So let me take this one out and let me now show the solution step by step. Okay, I will take this one out. Okay, so over here again, we like to design a single tone filter for the fifth harmonic, but as we explained it during the class, that we need to use not the fifth, we need to use the, let us say, to reduce it from 5 to 4.7 to prevent the filter frequency from shifting upward if one or more of the capacitor fail. Okay, so again, this is how to calculate the initial power factor or theta 1, as we did it already, and then we're gonna calculate theta nu, and then we're gonna calculate the reactive power or the size of the filter, okay, which is 398, and then we can calculate the value of XC and also of XL from here. So once we obtain QF, then we can obtain the value of QC as well. Okay, so we know that QC of course will be equal to QF time h square minus 1 over h square, like what we did it previously. So that will give us 380 kilovolt ampere reactive. So that will be the size of the capacitor bank. This is the size for the whole filter that consists of both, or that consists of both of L and C, but this is only for the capacitor. But now let us say that this is not available in the market. This capacitor bank, maybe it is not available in the market. So then let us choose, or what is available at that voltage level is 350 kilovolt ampere. So this is what we're going to choose, because this is the capacitor which is available. And now we're going to do the calculation based on this value of the reactive power that is supposed to be provided by the capacitor, or the size of the capacitor bank. Okay, so so to find XC, as we said, it will be V squared divided by Q. So V squared divided by Q, that will be the value, and then what is the relation between XC and XL? So XL is equal to XC over H square, so that will give you the value of XL. Okay, so now we determine the size of the tune filter. So what will be the component of XC? What will be the component of XL? Okay. But now what we like to do, we like to check whether the capacitor will fulfill the standard. So we need to check the root mean square voltage, we need to check the root mean square current, we need to check the peak voltage. So all those need to be checked whether it will be in line with the standard or not. So let us do it step by step. So this one will be the amount of the reactive power that will be delivered by the filter. Of course, now we should not forget that we choose the this filter according to the calculation. Okay, we choose that filter 398. Okay, but then and then we calculated the value of QC. We found it to be 380, but then we said that maybe this is not available in the market. Then we choose 350 kilovolt ampere reactive. So for that, if QC is equal to 350, so what will be the new value for QF? The new value for QF will be as it is given over here. Okay, will be 366. It will not be 398, because don't forget that we didn't choose 380 kilovolt ampere. We choose 350. So then we have to reflect the chosen one on the overall filter size. Okay, so that's why we recalculate the filter size or the reactive power that will be delivered by the whole filter. Okay, and we find it to be 366.6 kilovolt ampere reactive. Okay, so to find the to check that whether the capacitor can handle or will be in line with the standard. So again, we need to find the root mean square value for the current, root mean square value for the voltage for both the fundamental and for the fifth harmonic. Okay, so if we calculate the fundamental value for the capacitor bank, for the current that is flow through the capacitor bank and that is flow through the filter. So this is how can we calculate the current that is passed through the capacitor bank. So we know the size of the capacitor bank, which is already chosen to be 350 kilovar. We know the voltage, so that will give us the fundamental value for the current that will flow through the capacitor. And we can do the same thing with the fundamental current that will flow through the filter. It will be 440.95 ampere. Now for the to find the root mean square, of course, we need to find also the fifth harmonic, right? So to find the fifth harmonic current, he told us already that the fifth harmonic current will have a value of 30% of the fundamental load current, and the load current is already given to us. So then the fifth harmonic current will be equal to 421.5. Then what will be the root mean square current? The true root mean square current that flows through the filter will consist of the fifth harmonic current and the fundamental current that flows through the filter. The fundamental current that flows through the filter is 440, and the fifth harmonic current that flows through the filter is 421. Then the root mean square value of the current will be 610 ampere. Okay. Now to find what will be the true root mean square value for the voltage also across the capacitor. we need to find what will be the fundamental frequency voltage and what will be also the fifth harmonic voltage as well across the capacitor. So the voltage of the capacitor for the fundamental component will be equal to the current that passes through the filter times the reactance of the capacitor. So the fundamental current is 440.9. The reactance of the capacitor is already calculated and it was found to be 0.65, and that of course times root 3 because this is the line voltage, and that will give us this amount of voltage. For the fifth harmonic voltage, so we have to multiply the harmonic current times the impedance of the capacitor for the fifth harmonic. So that will be 96. Then now we can calculate the true root mean square value for the voltage, which will be the square root of that square plus this value square, and this is given over here. That will be 511.9. Okay. So now we calculated the true root mean square for the current that passes through the capacitor or the filter, because the filter it consists of L and C. So once we find the current that passes through the filter, that we find the current that passes through the capacitor bank. And we did the same thing with the true root mean square value for the voltage, and now we need also to calculate what will be the maximum voltage that will be applied across the capacitor. Okay, so as we said that the maximum voltage will be, we have to add the 2 root mean square current, we have to add the 2 root mean square voltage. So VC1 plus VC5, so this should be 5. Okay, so and that will give time root 2 to find the peak, and that will have 847. Okay, so that will be the peak value for the voltage. And also now if you like to calculate what will be the reactive power delivered by the capacitor now in this case, so it will be the voltage across the capacitor root mean square times the current that passes through the capacitor, and that will be 540.8 kilovolt ampere. Now let us check those value according to the standard. So those are the standard for the peak voltage, for the root mean square, for the root mean square current, and for the kilowatt. Okay, and this is the limit. For the peak voltage it has to be 120%. For the voltage, for the root mean square 110, root mean square current 135, kilowatt 135. But those are the actual value. So over here the actual value exceeded the limit, so this is not okay, this is okay, this is not okay, right? Because this is the root mean square, and this is the rated current of the capacitor 420, as we have already calculated that one, right? Remember, if you remember that we have calculated this one over here. Okay, that is the value of the current, the rated current that flow through the capacitor. Okay, so this is also not okay, that exceed the limit. If we look at the kilowatt, the calculated one is 540 and the rated is only 350, so that also exceed the limit. So therefore the capacitor that we have choose to be 350 kilowatt ampere will not satisfy the IEEE standard limit. Then what we have to do, we have, of course, since it does not satisfy the limit, then we need to to change the capacitor, we need maybe to choose not 350. So let us choose a bigger one. How about if we choose 500 instead of 350? And we choose 500 because also it is available in the market. If we choose 500, then of course we need to do again the calculation for XC with 500 and the calculation of XL. So we need to repeat the calculation again, and then we're gonna find also what will be the voltage across the capacitor, what will be the voltage, what will be the root mean square voltage, what will be the peak voltage, what will be the root mean square current, what will be the kilowatt. And then if we check that one, those will be the result. So this one, so if we choose that one, we're gonna find that this one will be in line with the standard. This is in line, that is in line, that is in line. Therefore, our selected or chosen size of the capacitor bank is fine. It satisfies the IEEE standard limit. Okay. And now if we like to check the following, because don't forget that this is our sketch for the circuit. So what we have now, we have over here our load, which will create harmonic. Okay, so we have a load that will create harmonic, because I'm trying to draw those for the circuit for the harmonic. So what I have a transformer with that impedance. Then I have my tuned capacitor, filter, single tuned filter. And I have the source of the harmonic. Okay, so this is our circuit, right? This one will be our circuit. To see, that is L, and this is the transformer, right? This is X for transformer. We'll call it X for. Okay, so over here I have a series resonance over there, and then between transformer and between the filter I'm gonna have parallel resonance, right? So now if I like to see the parallel resonance, if I like to find find the order of harmonic for the parallel resonance, what I have to do. So in parallel resonance we'll have XC. Okay, so to find the harmonic order, so I have XC and I have XL for the harmonic filter, and I have X for the transformer. I can check this one. Okay, of course XC it can be calculated, XL, X transformer is calculated from the initial parameter that are given in the problem. If you do the calculation, you will find that this one will be, the resonance will be at, or the harmonic order will be equal to 3. And of course I'm not producing my rectifier is not producing any third harmonic, so then I have no problem. If my rectifier is producing a third harmonic, it will be a disaster. Then I need to design a filter to get rid of the third harmonic. Okay, because if I have over here a third harmonic, and I have a resonance of my circuit is making also resonance at a third order, so that will be disaster. Okay, but unfortunately my rectifier is not producing any third harmonic. It produces only the fifth. So I have no problem. Okay, and of course if I check this one, if I check the C and L for the series resonance, that will be very close to the fifth harmonic. Therefore, the new value of C and L, it will take care of the fifth harmonic that come from the rectifier, okay, as it is shown over here. So I have no problem. Thank you.